Hello, and welcome to Differential Equations. This is Lecture 9, Higher Order Linear Equations. Last time, we talked about numerical methods. For first order ordinary differential equations. This time, starting to consider higher order equations. Okay, so let's start by recalling some notation. Right. So for the most part, we have been favoring the Leibniz notation, dy dt for derivatives, but sometimes it's convenient to use prime notation for the derivatives. So y prime of t would be the first derivative, the second derivative is denoted with two primes, right? The kth derivative in this notation would be y, and then we put parentheses and a k t. So the parentheses is so that we don't confuse this with y raised to the kth power or y composed with itself k times or anything like that. So we use these parentheses to remind ourselves that this means k derivatives of y. Okay, another notation we'll be using the summation notation, right? Where we abbreviate a sum, say a1 plus a2 plus up to an, right? We use a capital sigma with a counter. K goes from 0 to n, for example, a sub k. Okay, so with that in mind, the first thing we want to say is that the existence and uniqueness theorem for first order linear differential equations also holds for higher order linear differential equations, right? So theorem, existence and uniqueness. Okay, so here we want to consider the initial value problem of a nth order linear ordinary differential equation. Okay, so the general nth order linear differential equation, right? We can assume that the coefficient of the nth derivative is just 1. Then all of the derivatives before that have some coefficient, with coefficient function a sub k, and then the right-hand side, some function f of t, right? And so this is an nth order differential equation. So to set up the initial value problem, we need to know not just the value of y at t naught, right? Y naught, but also the value of the first derivative of y at t naught, which will denote y naught prime, up to the n minus 1th derivative at t naught, which will denote y naught n minus 1. Okay, so this is our initial value problem. And the theorem says that if the coefficient functions, well, if all of the functions here, right, so a k of t, right here, k goes from 0 to n minus 1, and f of t, if these are all continuous, on an open interval, containing E naught, then the initial value problem has a unique solution defined for all t in this interval, right? So remember, like we talked about when we saw this for first order linear differential equations, it's surprising and useful that the interval on which we know the functions are continuous is also the interval on which our solution is known to exist, right? For nonlinear differential equations, that's not the case. Existence and uniqueness just says on some interval, not necessarily as large as where the functions are continuous. Okay, so here the function f is known as the forcing term. Equations in which the forcing term is 0 are known as homogeneous. Otherwise, the equations are called nonhomogeneous or inhomogeneous. Okay, let's look at some examples. So if we have dy by dt minus 5t is equal to, sorry, minus 5y, say, is equal to t, then, well, this is one we've studied well already. This is a first order linear non-homogeneous, right? The coefficient functions are continuous everywhere. So given an initial condition, the existence and uniqueness are guaranteed on the entire real line. So from minus infinity to infinity, right? Suppose we had an equation like the second derivative with respect to t of y plus square root of t dy dt equal to 0. This is a second order linear homogeneous equation. This is the type of equation that we saw in a previous class you can reduce to a first order equation and solve. But right now, what we want to notice is that given an initial condition, existence and uniqueness is guaranteed on 0 infinity, right? Because the coefficient functions here, square root of t is only defined if t is greater than or equal to 0, and on that interval, it is continuous. Suppose for another example, that we had the initial value problem. Let's say that the fifth derivative of y with respect to t plus e to the t divided by t minus 2 times the second derivative of y with respect to t plus sine of t divided by t plus 1 times y is equal to 3. And in this case, we have y of 1 is, say, minus 2, y prime of 1 is 4, y double prime of 1 is 3. Third derivative at 1 is 0, and fourth derivative at 1 is also 0, right? So this is a fifth order linear non-homogeneous initial value problem, right? Non-homogeneous because the right-hand side here is not equal to 0. And we are given already our initial condition, so I don't need to put this conditional. So here we have existence and uniqueness guaranteed on. And so now let's stare the coefficients, right? This is continuous as long as you avoid t equal to 2. This is continuous as long as you avoid t equal to minus 1, right? Our initial condition is at the point 1, so the interval, largest interval where these functions are continuous and contains that point is the interval minus 1 comma 2, right? And that's where we're guaranteed to have a unique solution. Okay. So there are some remarks I want to make about linear equations of higher order. Okay, so first, just as for first order equations, we'll focus on the homogeneous case, right? Because just as for first order equations, if you can solve the homogeneous case, then you can use that to solve the non-homogeneous case, right? Also, as something we've mentioned before, is that often nonlinear equations are understood by using linear equations, right? So it's a good idea to get a really good understanding of linear equations, because that's useful not just when you're studying linear equations, but also when you're studying nonlinear equations. And then the last remark is that linear equations have a lot of structure related to linear algebra. Okay, so some concepts from linear algebra are going to come up in today's lecture and the next few. Things like linear combinations and linear dependence, determinants. Okay, so here is right away some of those concepts showing up. So this theorem is called the superposition principle. Okay, so consider a linear, importantly, homogeneous differential equation, right? Say nth derivative of y with respect to t plus some lower order terms, ak of t times the kth derivative of y with respect to t equal to 0. If y1 of t up to y sub m of t are all solutions to this equation, then any linear combination right? So what's a linear combination? It's you pick constants, multiply each one of these functions by a constant, and add those together. Right? That's what a linear combination of these functions is. Right? Any linear combination, right? So here, C1 through Cm are just constants. Is also a solution. Right? So this is called the superposition principle, because what it says is that if you have solutions to this equation, you can superimpose them, that is, take a linear combination, and you still have a solution to this equation, right? It's really important this is homogeneous. This is not true if the function is not, if the equation is not homogeneous. Okay, so why is this true? Well, the proof is very easy. I'll do the case m equal to 2, and let you write down the general case. The general case requires no more ideas, just a lot of more dot, dot, dot. So let's assume y1 of t, y2 of t are solutions. C1, C2 are constants, and let y of t be C1, y1 of t plus C2, y2 of t. Okay, so first notice that for any k, you take the kth derivative of y with respect to t. This is the same as taking the kth derivative of C1, y1 of t plus C2, y2 of t with respect to t, right? And, well, the constants just come out, and the derivative of a sum is the sum of the derivatives. So we just end up with the corresponding linear combination of the derivatives of y1 and y2. Hence, if we plug in y to the differential equation that we started with, right? Well, the nth derivative becomes C1 times the nth derivative of y1 with respect to t plus C2 times the nth derivative of y2 with respect to t, right? Then we have this sum, k goes from 0 to n minus 1, ak of t, and the kth derivative becomes this c times the kth derivative of y1 plus c2 times the kth derivative of y2. And then if we stare at this, we see that if you group all of the C1 terms together, we have dn of y1 dtn plus the sum k goes from 0 to n minus 1, ak of t dk y1 dtk. And then all of the terms with the C2, we get the same thing except evaluated at Y2. Okay, but now notice that this is exactly the differential equation we started with evaluated at Y1, and this is the differential equation we started with evaluated at Y2, but Y1 and Y2 are solutions to this equation. So that means that this is just C1 times 0 plus C2 times 0, so 0, right? And that's exactly what we wanted to show. This shows that Y is a solution to this equation. Okay. So for example, let's say that you were looking at the equation. Second derivative of y with respect to t minus 4y is equal to 0. Okay? It's easy to check that y1 of t equal to e to the 2t and y2 of t equal to e to the minus 2t are both solutions to this equation. The superposition principle tells us that for any constants C1 and C2, the function y of t equal to C1 e to the 2t plus C2 e to the minus 2t is also a solution. Okay, so now suppose we're given this equation with initial conditions. Right, so say we had second derivative of y with respect to t squared minus 4y equal to 0, and we were told y of 0 is y naught, y prime at 0 is y naught prime. Right? Can we solve this problem by choosing C1, C2 in our solution? Right? So here we wrote down that this function for any choice of constants C1 and C2 is also a solution, right? We have two equations here, and we have two constants. So it's very reasonable to ask, can you always arrange this initial condition by an appropriate choice of constants C1 and C2? Okay, well, let's just try, right? So since y prime of t is equal to 2 times C1 e to the 2t minus 2 times C2 e to the minus 2t, right? We have two equations. These two equations are y of 0 is C1 plus C2, and we want this to be equal to y naught. And y prime at 0 is 2C1 minus 2C2 equal to y naught prime. Okay, so we want to solve this system of equations, and it's easy enough to solve it just by staring at it, right? Because, for example, if you multiply this equation by 2 and then add it to this equation, you'll cancel out the C2s and you'll find C1. And if you multiply this equation by 2 and then subtract this equation, you'll get rid of the C1s, and you'll find the C2. Right? We can solve this with C1 equal to 2 times y naught plus y naught prime divided by 4, and C2 equal to 2 times y naught minus y naught prime divided by 4. Right? So if you have this initial value problem, it doesn't matter what values you give me here, I can find C1 and C2 that will satisfy these initial values. Right? Now, existence and uniqueness tells us that there is a unique solution. So because we've found a solution, we have to have found the unique solution. Right? So the uniqueness, the existence and uniqueness theorem tells us that there is exactly one solution to this equation, to this initial value problem. So we can conclude that every solution is a linear combination of e to the 2t and, well, in fact, let me write it like this. It's a linear combination of the set e to the 2t, e to the minus 2t. Okay, so that's wonderful. That's the sort of thing we want in general. We want to be able to find the general solution like we did for this problem. Notice that what made this work is that e to the 2t and e to the minus 2t are sufficiently different solutions of our equation. So sufficiently different, we mean there's no redundancy. Where we're headed is we want them to be linearly independent, right? But just for thinking about it now, we want no redundancy. So what do I mean by that? So suppose we had made a bad choice of two solutions. If we had used, let's say if we had tried to use the two solutions y1 of t equal to e to the 2t and say y2 of t equal to minus e to the 2t, right? These are two different solutions of this differential equation, right? However, they're not very different, right? We would not have been able to solve every initial value problem right? For example, we could not solve let's be very concrete about this. Let's say you want to solve y of 0 equal to 1, y prime of 0 equal to -2, right? If you take an arbitrary linear combination, call it a times e to the 2t plus b times minus e to the 2t, right? That's a linear combination of these two different solutions, but there's no way you can choose A and B to satisfy this initial condition, right? Since we would need right, y of 0 is A minus B. We'd need that to be 1, and y prime of 0, which is 2A minus 2B, would have to be -2, right? But notice that this left-hand side is just 2 times this left-hand side, right? So if this is equal to 1, there's no way this can be -2. Okay, so let's state our goal as a guiding principle, and we'll figure out how to do this next class. The guiding principle, if we can find n sufficiently different solutions to an nth order linear homogeneous differential equation, then the general solution will be a linear combination of those solutions, right? So this is just like our two solutions, e to the 2t, e to the minus 2t, for this differential equation give us all solutions by taking linear combinations. Our guiding principle is that that should be true in general, right? So we'll talk about that next time.